My name's Simon Jackson, and I'm going to be presenting today on numerical modelling for improved open pit optimization. So to start with, I'll just give you a brief introduction to me before trying to explain how open pit optimization works, and then we can look at how geotechnics and numerical modelling can be used to improve on the optimization process. So I'm based in the UK. I work for Mining One Consultants as a geotechnical engineer, primarily using numerical modelling to solve geotechnical problems, both open pit and underground. But really, I'm a mining and geotechnical engineer by background, so I like to try and think about how I can link the two together, which really got me onto asking the questions about how we can improve mining engineering by introducing more geotechnical engineering. So, open pit optimization, how does it work? It's used widely to establish early kind of pit shapes that can be used to guide mine design work. So the process, first of all, involves taking a block model, usually provided by a geologist, and that contains fixed information about what's in the ground, so grades, rock types, things like that. But it puts all that information into 3D space. Then step two is where the geotechs usually get involved, and that's to provide an overall slope angle. So that's usually a fixed number that can't be, it doesn't have any variable input. So it's applied based on domains, but really it's a very simple application of an overall slope angle. So we'll come back to that in a second. Next is the economic parameters. So that includes things like mining and processing costs, selling price of the commodity, everything needed to work out a cut-off grade. And in the background, the process or the software will assign a value to each block in the block model to establish its economic value. So then the overall slope angle is combined with those economic parameters, and it uses the information to actually waste stripping required to get to a block of ore. So if you think of it, testing this single block of ore here on the right with a 45-degree slope angle, we've got $100 of ore, and to get to it, we need to extract $75 of waste. So that leaves us $25 in profit. So that's good. So that's an economic pit shell. So then finally, there's some time parameters that go in. These are things like mining limits, throughput rates for the mill, and then those are combined with a discount factor to provide a kind of representative estimate of a project's value. In addition to this, there are some 3D wireframes that are output, nested pit shells, these are often called, and they represent economic shapes based on different commodity prices. So at a very low price, the smaller pit shells are generated, and at the higher prices, the big pit shells are generated. And those shells are developed for a range of values in between. So what's missing? The optimization algorithm itself is primarily working out what stripping ratio can be supported. But the quantity of waste stripping required really is controlled by the overall slope angle. So it's interesting that the slope angle is not considered an economic input. It goes in separately, can't be varied. There's no kind of additional detail that can be added to that. So I wanted to ask the question, is it possible to introduce more complexity to improve that overall slope angle that we're going to put in? And is it possible to then introduce more complexity in the optimization process itself, the economic side of things, to really provide better, more informative outputs from the optimization? And in order to do this, I didn't want to introduce a requirement for lots of geotechnical information. Usually, when a project is at this stage, there's not a lot to go on, and really you need to be able to develop this information using limited drilling or limited core logging, and maybe some test work. So traditionally, that's where slope stability curves have been very widely used. Generic slope stability curves, developed by Hook and Bray and adapted later by Reed and Stacey, they provide an indication of the stable slope height or slope angle based on the slope height. So here, well, that's great. It provides something to work with, which when you've got nothing, that's what you need. The trouble with these is that they are very generic. So there's no accounting for rock mass specifics. Here we have a plot on the right showing Kaman 2 copper mine, where Mining 1 has done some work. And the indication from this graph is that the slopes there would be highly unstable and inappropriate. But actually, they are stable modelling, and the actual excavation has shown to be stable. So really, you start to think, are these appropriate? And then more recently, we've kind of worked and developed some slope rock mass specific slope stability curves. So rather than looking at empirical case studies, we've just done some iterative modelling based on some kind of simplified inputs. And then we can develop rock mass specific curves to read the angles from. And that's really great because we can account for rock mass specifics and extremes, and using things like the improved unified constitutive model. We can do that with relatively little inputs, and we can be really highly confident in the replicating actual material behavior in the outputs. So in this case, I've used rock mass A from Tom Styles' paper. And when you look at the inputs required, we've got GSI with Brown constant, intact UCS, and the intact Young's modulus, which are very easily obtainable, or even using estimates of those. And from that information, run the iterative models and develop the curves here on the right. So if we look at a 600-meter slope, that's 45 degrees, that's great, we can use that for optimization. But then that's when we start to think, how can we improve the whole optimization process? And that's where we can say, well, what about if the pit shell was only 500 meters deep or 400 meters deep? And then we get different angles based on the depth of the pit shell. So is there a way to trick optimization into using those different angles based on depth? And yes, it is possible. There's a sort of a process is quite involved at this point, but it allows the angles to be dynamically applied based on the anticipated depth of each pit shell. And so I've turned this dynamic angle optimization just to make it easy to refer to. But you can see on this example what that would mean for the stripping ratio in those early pit shells. But note the final pit shell is still the same. So is it worth the effort to do all this? And to test it, I took a block model from the actual project and some generic optimization parameters. Then I used three approaches for the optimization. First, the generic approach using the Reed and Stacey graph. Second, the rock mass specific using the rock mass A Tom Styles from Tom Styles' paper. And finally, using the dynamic angle approach, again using the stability curves from Tom Styles' paper, but applying multiple angles through the process. Then we can compare the results. Mainly, we're looking at the ore and waste stripping ratio and the project value. So comparing the methods, moving to a rock mass specific approach really increases the project value, reduces stripping ratio, and that's what you can expect. Rock mass A indicates a much higher or much steeper slope angle than the generic slope stability curve. So you expect better economics from that. The difference between the dynamic angle optimization and the rock mass specific single angle approach is more subtle. However, much of the gain is made in the time value of money. The smaller pit shells that would be extracted first, kind of the early cutbacks, have steeper angles and better economics, but ultimately the final pit shells are the same. So that doesn't sound like it might be worth much. However, when you start to look at the scheduling, that increase in or reduction in stripping ratio in the early mine life can really have an impact on your income in those first years, where it's most critical to repay loans and get returns on investment. So actually, it can be very valuable to consider those more aggressive angles earlier in the mine life. So just to close, I think as we've developed better techniques for in geotechnical engineering, particularly in mining, it's beneficial to remember that they need to be applicable from a practical sense at all levels. So the development of these slope stability curves is a prime example. It's a way of introducing the complex constitutive models and kind of mold them into a format that mining engineers are comfortable with for use in kind of day-to-day studies and things like pit optimizations. So I think it's very important to keep in mind the development of tools for those applications almost as part of the ongoing advancements that we're making in geotechnics. And I'd also say that in this case, it'd be really beneficial to combine or couple the slope stability curve tools and the pit optimization tools so that they are almost seamlessly attached together, so that instead of a single stable pit shell, stable overall slope angle, you instead input some 4 or 5 geotechnical parameters, and the software develops those slope stability curves and runs a dynamic angle optimization based on that.